And the next speaker will be Joshua Cohen, who will tell us about OCaml APIs in Coq.
Hello, everyone. Hi, I'm Josh. As I mentioned, I'm going to talk about a little technique for implementing OCaml APIs in Coq. So the typical way to write code that you want to write in Coq, verify, and then actually run is something like this. You handwrite some Galena function, like say list append, and then you call the extraction mechanism. You get some purely functional OCaml program. And then since you probably want your overall program to actually have some sort of effect, like reading or writing from a file or printing to the command line or something like that, you'll handwrite some additional OCaml code that will do the I/O operations or stateful operations that will call your purely functional extracted code. And then you can bundle and link everything together into a single executable at the end. But real programs are more complex than this. There's more than just sort of defining executables that you can run from the command line. And especially in the OCaml world, most programs are built around using and providing APIs. So if I were to write a slightly more realistic OCaml program, I would do something like this. If I want to append two lists, I'd probably call something, say, from the standard library. And maybe I want to combine multiple libraries. I want, say, some map from the core library. I want some graphs from OCaml graph, et cetera. And as I mentioned, sort of pretty much every large-scale OCaml library and program is built around these APIs, even ones that are designed to be run as executables. So we have both libraries like base and core and batteries whose only function is to basically provide these APIs. But then even, as I mentioned, these executable programs still provide these APIs. So for instance, in the verification world, there's things like Frama-C, which is a verifier for C programs, or Y3, which is basically an intermediate language and a front end for SMT solvers, or Coq itself. All these programs are designed to be run as executables from the command line, but they also provide rich APIs for people to manipulate the kind of terms and formulas that you're using and to have more fine-grained control programmatically. And even things like, say, Z3, which aren't written in OCaml, might provide OCaml bindings for the same kind of reason. So we already know how we can reason about these kind of whole program executables, but how can we work with these APIs in Coq? So what we'd like to do is something like this, where we have an API implementation, and we can actually write down an implementation in Coq, extract to OCaml, and implement some existing interface. And this has the advantage where we can do things incrementally. We can look at parts of an API and identify the parts that are particularly, say, challenging to prove or interesting to reason about. We don't have to do everything at once. But we have a big constraint here, which is that we have to match the exact interface and the exact behavior that the OCaml client is expecting. And this turns out to be a big problem because, well, Coq or Galena, the functional language of Coq, and OCaml are very different languages. So for example, I show here a function from the Y3 API. As I mentioned, Y3 is this verification framework and this sort of front end for SMT solvers. And this is a function that creates an abstract function symbol declaration in their term language. And it's a pretty simple function. It has type L symbol arrow decal in OCaml, as you can see. But what is this function doing? Well, it does some error checks, and if there's some well-formedness check that fails, it'll throw an exception. And then it'll create the decal with that mkdecal function, which looks innocuous, but it's actually stateful. It's doing some hash consing. And of course, because we're in OCaml, none of this is reflected in the type. So if we're interpreting this L symbol arrow decal as some Coq type that we're trying to implement, this is a pure function that takes in an L symbol and must return a decal, when really the function that we want is a program that might throw an exception, it might give us a decal, but also modify some global state. So we can't really represent this using the same kind of Coq type. And there's a lot of features that fall into this category where we can't implement them or we can't implement them idiomatically with the same type in Coq. I'm going to focus in particular in this talk on exceptions in immutable state, but there are many others as well. And a key constraint that we have for sort of a particular application that I am using this for is that we want computable code in Coq. So we want to be able to do things like proof by reflection and to actually use like simplification and things like VM compute and so on this code to enable to take advantage of the nice computation capabilities that Coq has inside the proof assistant, which means we don't want to just like axiomatize all of the OCaml behavior. All right, so there's a lot of ways that people have thought about how to do this, and I'll talk about some of them at the end. Most of them tend to be quite heavyweight, and we sort of take the exact opposite approach. We take emphasizing this lightweight and pragmatic sort of methodology. And the key idea is to represent these features differently on both sides in Coq and in OCaml. And we link them together in a careful and principled way by modifying the extraction. And so we propose in this talk a sort of design principle for this idea. And if you are interested, I'll put a link at the end. There's a repository with some examples and a little library to enable programming with some common OCaml features. So let's look at an example of how this works. And let's look at the list.head function from the OCaml standard library. So this is a function that if you give a non-empty list, it'll give you the first element. If the list is empty, it will throw an exception. It has type tick a list arrow tick a, which of course is not representable in Coq. This would be very bad if we could write such a function. And but this is sort of the API that we want to implement. And the idea is that even though we want an OCaml implementation that uses exceptions, in Coq we're going to model this using an error monad. And so how does this work? Well, the first thing we do is we model exceptions in OCaml as a type in Coq. So we have this record error type, which just has a name and some arguments. And we can define specific models of exceptions, like say failure, which just at the bottom there, which just takes in our message. And then we define our monadic interface in Coq. So this is using the CoqXlib library, which has a whole bunch of monads and monadic interfaces. And so we can define our error monad as just the sum type that's either the exception model or a successful return. We can use from CoqXlib things like return and bind and throw in exception, which just gives the error case. You can also add things like try catch. For instance, this is just a simplification for the talk. And then the key part is that we want to extract this to an interface in OCaml that uses exceptions. And so we're going to erase this monadic interface when we extract. So our error MA, our error monad, just becomes type A. Our error type becomes exception, as we intended. And then we sort of push the types through all the monadic operations. So like return, for instance, in Coq has type A to error MA. And when we erase the monads, that's just A arrow A, which is the identity function, and so on. And then for specific exceptions like failure, we interpret this just as the OCaml exception failure. And now we can implement a function in Coq that lives in this error monad for the head. So we have a monadic return type. In the case where the list is empty, we have this throw, which again is just giving the error case in the monad. Otherwise, we return. And with this modified extraction, when we sort of turn the crank, we end up with the function in OCaml that we wanted with the type that we want and the behavior that we want. And so this kind of defines the recipe for doing this, where if we have some OCaml feature that we can't represent in Coq, we want to figure out a way we can model that kind of feature in Coq, identify some set of primitive operations to interact with this interface, and then map those primitive operations to OCaml. And as long as the Coq clients are only using the primitive operations to interact with that interface, I'll talk a little bit more about that at the end, then you get a lot of nice properties where your Coq code you can fully compute. It's similar to the code you would have written by hand. You can prove things about it as normal, and we don't have any axioms. There's no we're not sacrificing anything on the Coq side. Meanwhile, the OCaml code you get is computable. It has the right interface that we want, and clients can use the code. It doesn't have monads, for instance. All right, so mutable state is a little bit more complicated. We start with the same basic idea, where we're implementing it in Coq with a state monad and OCaml with a mutable reference. And so again, we're going to extract this monadic interface. If we have our type state AB, where our state type is A and our return type is B, we just extract a B. We can sort of do the same kind of thing with return and bind. Now, because we're in a state monad, we have get and set, which we interpret as getting the value and setting the value of the mutable reference. And because we need to know which mutable reference we should actually be looking up, we encapsulate this in a module and make it so you can create a stateful computation in Coq or a mutable reference of any type. Now, the problem is that this isn't actually sound if you do this naively. And the problem is that the state monad is, at least morally speaking, a function. So we take in our old state and produce a new state in our return value, which means we have some way of applying this stateful computation to an initial state, which we can call run state. And if you imagine extracting this run state function, once we erase all the monads, in OCaml we would get this type like tick B, arrow tick A, arrow tick B. And the only reasonable thing we could do is just return the first argument, which is saying that we should ignore the initial state. And in OCaml, this makes sense because we already fixed the initial state. We created the mutable reference with some value. And if we were to instead say we want to run our whole computation with a different initial state, that's like going back in history and saying, well, if we had instead just instantiated this mutable reference with a different value and done everything all over again, here's what we would have gotten. And we can't do that. This is unsound. So a solution to this is, well, we can just fix the initial value. So our state module that I mentioned before is parameterized by this module type that includes both the type of the state we want, as well as the initial value or the default element. And then our run state function that we provide does not take in an initial state. It runs it starting from that fixed initial state. And in OCaml, we implement this by resetting the mutable reference to that initial value. So we can rerun the stateful computation as many times as we want in Coq or in OCaml, but either way, it's always going to start from the same value. And so, all right, we have these stateful computations and things like that. Well, how can we reason about this in Coq? So to show this, I gave an example in the repository of a small integer term API. So basically, we have some integer operations, as well as variables, bindings, like let bindings and variables. This is inspired by the Y3 term API, but it's a much simpler and more general kind of case. And our variables and our bindings are abstract. So the way that this API works is the only way you can create these variables and bindings is with these functions here. And there's some global mutable counter that's generating fresh variable names every time you want to like substitute under a binder. So you can implement substitution statefully, but safely using this alpha conversion. And to prove things, like to prove the correctness of this substitution, we can use some ideas from the Hoare state monad from about 15 years ago, which you can basically think of as like a shallow embedding of Hoare-style reasoning in Coq about these kind of state monads. The exact definition on there is not like super important. The original paper kind of presents this in a dependently typed way, but we have like a non-dependently typed version, and we provide some useful sort of lemmas and ways to reason compositionally. And we can use this to prove the substitution function correct. So we have a theorem that says something like, if our input is well-formed, which means that all of our variables were created by the API, after we run this stateful computation of substitution, we end up with the result we expect, which is it's the same thing as just like adjusting the variable valuation appropriately with the substituted term. And all of this reasoning is like just basic Coq reasoning. We don't have any like deeply embedded program logics or anything like this. The state Hoare monad is really just like a nicer way to organize these kind of proofs, but you're really just reasoning in the core logic of Coq. Now there's some limitations to this approach. I'll talk about a few of them. I won't have time to talk about all of them, I think. There's some issues with sort of scalability. So like for exceptions, for instance, we need a new, every time we want to model a different exception in OCaml, we need to define the model that in Coq and extract it to the corresponding exception. There's some Dune preprocessing. All this stuff I think could be automated, but right now there's a little bit of manual work in there. And of course, you have to trust the modified extraction, which is intended to be sort of small and something that you can easily kind of look at yourself and maybe not too controversial. But I'll talk a little bit more about that later. But yeah, that is more trust on the OCaml side. But the big limitation, the thing on the last bullet here, is due to limitations in the way that Coq handles opacity, we can't enforce this restriction that the Coq client is only using the interface. So for example, say you're in the error monad case. If you take your something in the error monad and you pattern match against it, that's perfectly fine in Coq because it's just a sum type. But in OCaml, now you're trying to pattern match on an exception and treating it as a sum type, which is going to cause type errors and all sorts of problems. And so unfortunately, this is a limitation at the moment. There may be some ways around it thought about, but it's ultimately up to the user to make sure that they're using the interface correctly. And so there's a lot of work in this area about connecting imperative code and functional code and reasoning about imperative code and proof assistance from things like Why Not a while ago, about a framework, a sort of heavy-duty framework for embedding imperative programming reasoning inside Coq, which axiomatizes the stateful operations. Then there's more recent work like iTrees, where you can model impure code using a co-inductive monad, which means you can't necessarily compute everything in Coq from the co-induction. More interesting, these last three. So there's some similar work in CoqML, so you can implement some monadic functions to Hall and sort of synthesize stateful CoqML functions with some proofs. And some ideas from that would be useful for proving this correct if we had an appropriate semantics for OCaml. There's also formally verified defensive programming, which allows you to, in a safe way, to call OCaml code from Coq, and it uses this may return monad. So this would be useful to extend this with, like, you could have OCaml APIs where you implement part in Coq, but part of it also depends on some external OCaml code that you can verify the correctness of. And there's also VeriFFI, which was presented just a few days ago at POPL, which is a verified foreign function interface between Coq and C, so you can call C functions from Coq. And it solves this opacity issue that I mentioned by basically axiomatizing the external functions and providing some isomorphisms and rewrite rules. So some of these ideas I think could be used to extend this to sort of eliminate some of those limitations that I mentioned earlier. All right, so to wrap up, we present this approach that really aims to be lightweight, practical, to minimize the burden on the user, while being able to do a little bit better than like handwriting your OCaml APIs. And you get programs that are executable in both Coq and OCaml. They're reasonably idiomatic in both languages. They're usable by clients in both languages. And on the Coq side, we can reason about them in Coq, in ordinary Coq tactics and logic. As I mentioned, there's this repository available with some of these more involved examples. And yeah, thank you for listening. I'll now take questions.
We have time for some questions.
I'm wondering how you would approach verification of a pipeline like this. In particular, it seems like it would be intrinsically non-compositional in terms of like when you're adding things, you're redefining what exon means every time, right? And that would have problems for being able to say how, if you're using like two variations on this extraction, like, you have two clients that have used your method, then having a verification, you would need some global view of everything in order to do a verification. I don't know, what are your opinions?
I'm not sure I completely understand. I mean, the things like the exception stuff, we only have to define those once and to define the extraction commands once in some sort of like generic library, and you can just use that. If you have a particular like new exception that you want to add, like there was failure here, but you could add many more, those ones, like each time you have a new one, you have to add it, but you only have to add that. You don't have to like go and redefine everything. I'm not sure if I answered the question or.
So, well, I guess the way you originally presented it seemed like every client would be defining what exception.
Oh, no, sorry. This was just an overview of how the thing works, but really all the error monad stuff, the error monad interface is sort of generic. The only thing that you write each time by hand would be like the head function in the example.
I'm still a bit confused about this initial value thing with the state. Like, it seems if I run the computation once, that may change the state.
Yeah.
And then if I run it a second time, something has to reset it somewhere.
Yes.
Right? Where is that happening?
In OCaml, you think? Or
yeah, and which of these APIs is doing it? And
Yeah.
if there's an API that can do that, why can't this just change set the initial state to whatever I'm setting it at without, like, if it can reset it to the original initial state, why can't I pick this every time I run the computation?
well, I mean, you could, but just by running a set before any other computation, before anything else you're doing, I guess. You could always set the state before anything else. So in this interface here, like this run state function is extracted. I didn't show what the extraction looks like, but it's extracted to something that basically returns nothing useful in OCaml, but just resets the value of that initial reference. And then the user is always free to set the state to whatever they want by just using the monadic set operation. But we just give this default initial state because otherwise, like in Coq, you could, like say you have some counter and you have an inker function and you could prove like, that inker starting point 1 equals inker 1 or whatever. But if you run inker twice in OCaml, that does like have an effect. You can't just prove that they're equal. That makes sense.
I don't think I really get it, but maybe we'll ask
Okay.
again later. Thanks.
Okay.